Alright, here's an example on how to do concavity with the trig function. So the function's a little bit more involved when you get to the derivative, but still the same thing, and you got to remember how to take solve a trig equation, especially when you have something other than x inside of the trig function. So first thing, if we're going to do concavity, we need to go down to our second derivative, because the first derivative tells us increasing and decreasing. The second derivative tells us concavity. So let's go down the first derivative. It'll be 2 constant multiple rule times negative cosecant of 3x over 2 times cotangent of 3x over 2 times the derivative of the inside, which is 3/2. If I simplify the derivative, and I probably should do that before I go any further, the 2's are going to cancel from the 3/2 and the 2. I can bring that 3 out front, and it's going to be a negative 3 cosecant of 3x over 2 times cotangent of 3x over 2. Now when you go to the second derivative, it's going to get a lot more involved because we're going to have to start using the product rule. So again, we want the second derivative because first derivative tells us where we're increasing and decreasing, and it tells us relative extrema. The second derivative tells us concavity and points of inflection. So now we're going to do constant multiple rule again, so we're going to have negative 3 times. And what I'm going to do is I'm just going to take that negative 3 and multiply by it at the very end. So we're going to have the derivative of these two things using product rule. So we're going to have negative. So let's start with, we'll do this one in red. So we're going to have negative cosecant 3x over 2 times cotangent of 3x over 2. Oops, I need to erase that and make that a little bit better. That's cotangent, not cosine. So times cotangent of 3x over 2. Might run out of room here. Times 3/2, and then times the first function, which was, or the second function, which was cotangent of 3x over 2. So right here is here's the derivative of the first, this part right here, and this was times the second function. Now we got to go plus, and I'll change to blue. Now we're going to go the derivative of this one, which is negative cosecant squared 3x over 2 times the derivative of the inside, which is 3/2, times, I'm going to have to come down on the next line here, times the first function, which is cosecant of 3x over 2. So again, that was the derivative of the second function times the first. And so now I'm going to simplify, and I'm going to try and combine some things. And this first big thing right here, I can combine the cotangents, and I can bring the 3/2 out front with the negative, and I already have this negative 3 out front. So it's going to look like this. My second derivative, okay, is going to be a negative times a negative, which is a positive. We got 3/2 times 3, so this 3/2 times 3 is going to be 9/2, so positive 9/2 times cosecant of 3x over 2 times cotangent squared of 3x over 2. Okay, now we're going to go to this next part, and we have a negative times a negative, a positive and a negative, but there's a negative there, so negative times a negative is going to be a positive. There's a 3/2 again, so it's going to be plus again, and it's going to be 9/2. It looks like again, because we got this 3/2 right here, so it's going to be a positive 9/2. We're going to have cosecant, it looks like cosecant to the third, 3x over 2. I believe that's right, because we got a cosecant squared and then we got a cosecant. That looks good. Now we're going to factor, because the next thing we're going to want to do is find critical values. But before we do that, let's go ahead and factor. We can factor a 9/2 out, and we can factor a cosecant 3x over 2 out. And then what we'll be left with on the inside is going to be cotangent squared 3x over 2 plus cosecant squared 3x over 2. Okay, so the next part is where this gets pretty interesting. Let me undo what I just did there. see here. Let me go and erase that part right there. That line. Okay, so the next part's where it gets pretty interesting. So I'm going to scroll down. I'm going to move this down. I'll be up on top of my problem a little bit, but that's okay. So I'm down here to the second derivative, which is what I want. Alright, so here's my second derivative. So now I'm going to take this part right here, and we want to figure out where it's undefined and equal to 0. So let's start where it equals 0. The undefined stuff will just kind of f prime 0, so 2 with the 9/2 out front, but Alright, so I finished solving it. I actually factored it. Sorry, I came back. I just went ahead and solved it, and then you can look at the work, and I'll explain it now to you guys. So what I did here is I found out, first of all, where f prime is equal to 0. So I took this part right here. I set it equal to 0 right here. Divided by the 9/2, got it to equal to 0. Then I went 1 over sine of 3x over 2 equals 0. But since the top can equal 0, this whole fraction can equal 0, so there's nowhere where it equals 0 in this first part. But then I went to undefined. Now this is the tricky part. I took the inverse sine of both sides. You can see that. It cancels the signs out. We get 3x over 2. Now here's the part you probably don't remember. We did this first try, but inverse sine of 0 is 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. But since we haven't solved for x over here, we don't know which value you want. So you're going to just kind of have to list all solutions first. Then we have to completely solve for x, and then we'll go locate the values between 0 and 2 pi. So since we know it's 0, pi, 2 pi, 3 pi, we know all the solutions is pi k. So then I'm going to solve, multiply both sides by 2/3. We get x equals 2 pi. We get x equals, let me write that again, 2/3 pi k. Then you start plugging in values for k that will give you values between 0 and 2 pi. So we start with 0, we get 0, but we don't want to include 0. So we're going to throw 0 out. Then we do 1, we're going to get 2 pi over 3, and then if we do 2 for k, so again, if I put, like for example here, if I put a 2 in for k, you're going to get 4 pi over 3. Then I took this part, and I set that equal to 0. And let's solve where that equals 0. Well, this plus this, I went ahead and wrote as cosine. What I did is it ends up being cotangent is cosine squared over sine squared. Cosecant squared is 1 over sine squared, but it's of the same angle, so it's cosine. Sorry. Cosine squared 3x over 2 divided by sine squared 3x over 2 plus 1 over sine squared 3x over 2 equals 0. Then since it has a common denominator, I looked for where the numerator is going to equal 0 right here. But when I solve it, I get cosine squared 3x over 2 is equal to a negative, so you're going to take square root of a negative. So we throw that out because they're imaginary. The bottom equal to 0 is where it'd be undefined, but we already did that with sine 3x over 2 equal to 0. So our only solutions here are going to be 2 pi over 3 and 4 pi over 3. So I'm going to let you finish this. You would do your sign analysis at this point, and you would have to set up your, you'd go 0, I'll write that at least for you. You're going to go 0 to 2 pi over 3. You're going to go 2 pi over 3 to 4 pi over 3. And then you'll go, I guess I could just go ahead and at least get that set up for you. 4 pi over 3 to 2 pi. And you're testing the second derivative, so make sure you plug it into the second derivative, which is right here. Now, the nice thing about this, if you think about it, this right here is always, this part, I'll circle it in black right here, is always going to be positive because you're squaring. After you plug in your angle here, you square it last. And since you square it last, it's always going to be positive, and you're adding two positive numbers. So this will always be positive. So you only need to check the first one. So you're just going to plug in a value. And I would pick something between 0 and 2 pi over 3. I'd pick like pi over 3. And so if you pick pi over 3, if you plug pi over 3 in right here, you're going to end up with pi over 3 in is end up being, because of the 2 in the denominator, it's going to end up being pi over 6 times 3. So pi over 6 times 3, or think of it, if you plug that pi over 3 in, look at it like this. We know it's going to be pi over 6, but those 3's just cancel, so it's really just pi over 2. Cosecant of pi over 2 is 1 over sine of pi over 2. Sine of pi over 2 is 1, so 1 divided by 1 is 1. And then 9/2 times 1 is positive, so we know this first one's going to be positive. And it should alternate signs because there doesn't appear. You better check this one to make sure, but it should alternate signs. Let's see, we got a sine to the first and a sine squared. Yeah, it should alternate signs. So we should be okay there. but you can check it if you want. You could do pi. Between 2 pi over 3 and 4 pi over 3, we could do pi. And if we do just pi, we're going to get 3 pi over 2. Cosecant of 3 pi over 2 is -1. Yep, that'll be negative. So then we know it's concave up, concave down, concave up. And then our POIs would be, because it changes in concavity, a POI would be at 2 pi over 3 and 4 pi over 3. And you plug it back into the original equation to figure out what the values actually are. So if I go back to the original, f of, let's see here, I'll just finish it for you, f of 2 pi over 3. So this is a fairly involved problem. 2 times cosecant of 3 times 2 pi over 3. And it's divided by 2, so you can just put the 2 on the bottom with that 3, so it's going to be a 6. Well, the 2's and the 3's are going to actually cancel, so you get cosecant of pi, which is 1 over sine of pi, which is 0. 2 times 0 is 0, so that first one's going to be 0. So there's the first critical value. I'm guessing that 4 pi over 3 is going to be the same thing, but we'll see. So we have 2 times cosecant of 3 times 4 pi over 3. And if you don't like what I did before, you can just do it like this. I would go ahead and put this 3 right here in the denominator. It's going to get moved to the denominator anyways, because when you divide by 2, you're multiplying by half. But those 3's are going to cancel. So we're going to get 4 pi divided by 2, which is 2 pi. Cosecant of 2 pi is also going to be 0, and 2 times 0 is 0. So it looks like the points of inflection both are on the x-axis, which kind of makes sense because trig functions are periodic. So there you go. There's an example to look like with a trig function.